Testing. Okay, so what I'd like to do in this video here is just to give you a bit of perspective on how you can handle all this, making these collision animations. So what I'd like you to understand is that the problem is really the following here. If we go back into Megapov just for a second here, I have some code going here which just sort of illustrates the problem that we're sort of facing here, in that there's two balls, a big red one and a big yellow one, that approach each other here, and they just go right through each other. And we'd like to address this issue of what do you have to do to make this interaction happen, which is going to be a collision. So what I'm hoping that you sort of get out of this discussion and this theory here is that we're really dealing with the same problem, aren't we? Like, here's two balls with an M1 and a V1 moving towards each other, and when they get at closest approach right there, you need to do something about this, because that's what the collision is. They need to bounce off each other. The equations of physics don't allow objects to know about each other, so as far as the equations of physics go, this M1 is going to keep going right through M2, and this M2 is going to keep going right through M1, but you want to stop that from happening. So we really have three collision so-called responses that we're dealing with in this class. One is this impulse mode, where we calculate the J. The next one is the inelastic collision mode, where things stick together and form a blob after a collision. And the last one is the elastic collision, where things bounce off each other like springy balls and that kind of thing. Very rubbery, very idealized collision. And so hopefully what you can understand is that you have three so-called collision responses. There's the impulse one that gives us the delta V's directly. These delta V's are important because something has a V1 going into a collision or a V2 going into a collision. This equation tells us how those velocities must change in order to allow the collision to happen properly. Delta V, V1 must change by the amount J over M1. V2 must change by the amount J over M2. That's one way of responding to a collision. But of course, you don't have to know what J is. But if you look in the description for the movie that talks about this impulse collision, there's an equation for J in it, which you should use. In the inelastic collision, again, two things are hitting each other. They're at closest approach, but they stick and form a big blob. A very straightforward conservation of momentum equation will tell you that M1 V1 minus M2 V2, this is the initial momentum of the system along the x-axis. That's all equal to the final momentum. You can just solve for that outgoing speed of the blob. In the elastic collisions, if you look in my book, the very last sentence of the momentum chapter under the physics there's some equations that look like this. They're very long and very ugly, but look what they do. If V1 and V2 are the speeds before a collision, you have a V1 after and a V2 after. The elastic theory tells you exactly what the speeds of objects need to be after a collision to allow that collision to happen properly. If it's V1 before the collision, it's V1 after the collision, V1A. If it's V2 before the collision, it's V2A after the collision. And notice they're functions of the masses and the ingoing speeds. That's just the way the theory is. So if you can just step back and look at the computer work that you have in front of you, then it's really a matter of just implementing three different collision responses for the exact same systems. So let's see what we can do here in our code. If I go back to the Megapov, this is the code here that just sends the balls going in towards each other that I just showed you. No big deal, and they pass right through each other. So what we'd like to do now is observe in the last video that we really need to be working down here in part 8 of the skeleton code, because this is where we can put in abrupt changes in velocity to make these collisions happen. So a couple things you have to do. We discussed this in class, but one thing you have to be aware of is, well, how close are the balls together? If I go back to this image here, you can see all of these balls at closest approach. There's the M1 and M2, and the M1 and the M2, and the M1 and M2. They're at closest approach, and if you can imagine, well, how close are they allowed to get? Well, if this is the center of M1, if I go all the way out to the edge, that's the radius of M1. If this is the center of M2, that's the radius of M2. Clearly, this distance of closest approach is just the sum of the radii of the individual balls in there. So if I go back to my Pavre code and look around what I have some masses, positions, velocities, and even radii declared up here. Now I'm being kind of silly here. I'm actually declaring the radius just to be equal to the mass. I know those aren't the same physical units, but at least allows my drawing of these spheres to take the size of the mass. So the larger the mass is, the larger the radius will be. I do the same thing down here. And I'm also being very careful to remember, if I'm going to define these radii here, then to use the R1 and the R2 down here in the sphere drawing statements. Don't leave a 1 and a 2 in here if you're going to define the radii like that. So what I'll do then is to see, are these balls here approaching, or are these spheres approaching their closest approach? Let's calculate the distance between them. And that can come very easy from doing something just like this. V length of pose 1 minus pose 2, something like that. Remember, pose 1 and pose 2 are the instantaneous vectors about where these spheres exist in space. If I just subtract them, I get the vector difference between them. And if I tell Pavre just to give me the length or the magnitude of that vector, then d now is going to be the scalar measurement of how far the two balls are apart. And that's exactly what I need for this collision detection. So what I do now is I just start some big if statement. I say, look, if D is less than or equal to R1 plus R2, and remember, I need to have those radii defined somewhere. These need to be defined somewhere. If this holds, then the balls have reached that closest approach position, but this is not sufficient enough to make a collision come off. How come? Because remember, initially, M1 is moving to the right, has this positive 10. M2 is moving to the left, has this minus 20. Those are the velocities that are sending the balls into each other. So before I decide to respond to a collision, I have to make sure the balls are actually heading towards each other, because they could be near each other and moving away from each other. I wouldn't want to do a collision then. A little and statement will handle that. I'll say if vel1.x is greater than 0, that means that first object is still moving towards the right. That's greater than 0. And vel2.x is less than 0. That means the other one is still moving to the left. This is the proper collision detection you need. It checks two things. It checks the proximity of the balls. They have to be close to each other. And it checks the direction they're traveling. Is this one traveling to the right? Is this one traveling to the left? If that's true, then we're ready to respond to a collision. So I'll go ahead and put a little end statement in here, because I know if statements always need to end with those end statements in there. Now all I'd like to do is just go ahead and respond to my collision. If I'm going to do collision 1, the very raw collision, I'm going to need that impulse in there. So I'm going to have a declare statement, J equals something in there. And you can fish that J equals statement out of my book there. It tells you what the impulse should be for reasons to keep things a little less random. We don't want you choosing forces and collision times. There's something you can choose for an impulse in there that has to do with the coefficient of restitution. So you can put that in. But hey, once you have that, you need to send velocity 1 out of the collision. So you can say, look, vel1 is equal to vel1 plus J over M1. Something like that. And that is exactly this theory, which was I was trying to tell you. V1 has to change by this amount to carry it out of the collision. And the amount is the impulse divided by its mass. And the same thing happens for the second mass in there as well. You can send that one out of the collision like this. Vel2 is equal to vel2, say, plus J over not M1, but M2 now. Each one carries off its own mass. And if you do this, this is essentially all you need to do to handle that raw collision. You have your impulse, which has to do with the force that is between the two spheres when they're touching each other, and now you just need to make a big correction to the velocity. Say, yeah, I know the physics equation wants you to head towards each other, but we need you to go away from each other now. You need to correct the velocities. Now, the only last thing you have to sort of mess around with is remember that these equations here for the impulse, it's a Newton's third law thing. One gets the positive impulse, one gets the negative impulse. That's Newton's third law, equal and opposite forces. So you might have to play a little bit around with your signs in here, like maybe this one's supposed to be negative and that one positive, or it could be that one has to be positive and that one has to be negative in order to get the collision to work out right according to Newton's laws. I'm just looking at it here thinking it is a bit difficult, hard to say exactly what's going to happen, but you just need to twiddle those signs. But see, those three lines, actually this group of lines right here in part 8, will handle your raw collision. And in particular, these three lines right here handle the impulse. Suppose you wanted to move on to the inelastic collision now, where the blobs stick together. Everything is going to stay the same. You still need to compute this proximity here. You still need to see if the spheres are near each other. You still need to make sure they're moving in the right direction, that is, towards each other when the collision occurs, but you don't want to use the impulse anymore. You have another theory you're testing, which is the inelastic collision theory. But if I go back to this sheet, the velocity is given to me. Simple equation you can find in your book and you're using to solve your homework problems with. Here's the outgoing velocity of the two balls as they stick together. Why don't we just put that in? Why don't we just say capital V is then equal to M1 times vel1. There's that ingoing momentum of the first ball. Minus M2 times vel2. There's that ingoing momentum or velocity of the second ball. Now I need some parentheses in here because this was supposed to be a big numerator. So I'll go here and here with it, and I'll just divide that thing by the sum of the two masses. This equation is exactly what is predicted by inelastic collision theory from your book. P initial equals to P final. I can solve for V. Now you want to make them stick together. Do you have to do some fancy gymnastics or special coding to make them stick together? No. You just have to assign both of the objects that same velocity as they leave the collision. And if objects have the same velocity and the same acceleration, they will always stick together, and that's exactly what the inelastic collision predicts. And so I hope you can see the similarities and sort of the consistent structure among the work that you're being asked to do here. All of this stuff stays the same. What you're just changing are the guts of this here to have the different collision responses each time. And in the last collision for the elastic one, where you want things to bounce off each other, it's once again, let's get rid of the guts. because now we're in elastic mode, where things bounce off each other. The elastic theory are these equations here, which you can find at the very end of my physics chapter on momentum here, or they're also written down. So yeah, you'll have to program these big formulas in because they tell you what the post-collision velocities are, the v1 after and the v2 after. Now I'm not going to do that fully here, but I'll say something like this. v1 after is equal to, I think it was, if I go back, sure, m1 minus m2 times v1, or vel1, pardon me. That's the velocity the object has before the collision. And now you can put in the rest. There's going to be a plus and some blah, blah, blah here. You can put the rest of the equation yourself. And you can do the same thing down here for v2 after. And just to get the first term started, it looks like it's a 2 times m1 divided by m1 plus m2 plus blah, blah. Now these might not be right. In fact, I'm looking at it going, I probably need a divided by m1 plus m2 in here to get the equation right. But you'll make sure these are right. Now there's one other caveat. Well, before I tell you about the caveat, let me just continue then. So we have our v1 after and our v2 after. And once we're sort of done with that, now that we know the outgoing speeds, why don't you just assign those speeds to the objects themselves? Why don't you just say vel1 now is equal to v1 after, and vel2 is equal to v2 after. This theory tells you what the outgoing speeds are. So once you compute them, just assign them to the velocities, the ongoing velocities of the object, and you'll have your elastic collision happening for you. It's pretty nice and consistent. Again, what stayed the same? The proximity and the collision detection. All your changing of the guts here. We've changed the guts 3 times. Impulse, inelastic, and now elastic. And you should be all set.